Hello everyone, my name is Varat Tau and I am a doctoral student at the Department of Chemical Engineering at IIT Kanpur. I welcome you all to the first lecture of this class of this chapter, that is structure of atom. So this is uh, a class 11 second chapter of chemistry of NCERT syllabus. So I'm planning to cover this chapter into 12 weeks or 12 classes. Each class will be 1 hour class, and in each class I will be teaching concepts. So concepts, and then concept based questions, which you can also say as DPP, daily practice problems. So this I will be giving at the end of each class, uh, which you have to solve and come in the next class, and if you have any doubt you can ask me. So with this, let us start. Okay, so structure of atom. Okay, so everything around us, whatever you see, those are living beings or non-living things, a piece of wood or a piece of metal or a stone, or even the dress which you are wearing or the food which you are eating, everything around us is made up of some fundamental particles, right? So you can think it in this way, that you take, let's say for example, you take an iron rod and you break into two pieces. Again, those two pieces can further be broken down into two pieces. These two pieces can further be broken down into two pieces, right? So a point comes wherein this we cannot break down. A point comes where a material or a substance cannot be further broken down. This is what is called as the Greek word for this, atomos. Greek word is atomio, and the Sanskrit word is
क्या आप सुन पा रहे हैं?
yes, yes. आप सुन पा रहे हैं मुझे?
यस, तो एक रिक्वेस्ट थी आपसे, जो आप इसको शायद आपने पोर्ट्रेट मोड में रखा हुआ है टैबलेट,
ओके ओके
इसको आप लैंडस्केप में कर दीजिए या फिर समझ गए ना, आप लैंडस्केप मोड में रख लीजिए। अब पढ़ाइए। अगर रेज़ोल्यूशन इंक्रीज़ करने का ऑप्शन है तो भी कर दीजिए और फिर से पूरा एक बार एक्सप्लेन कर दीजिए।
फिर से ओके ओके ठीक है।
ठीक है? क्योंकि वो रेज़ोल्यूशन हम नहीं ले पाएँगे, एक्सेप्ट नहीं कर पाएँगे इसलिए।
ये जो रिजोल्यूशन है ये चलेगा क्या? अभी मैं लैंडस्केप
अगर
कर दिया।
अगर इससे आप बेटर कर सकते हो तो ठीक है, नहीं तो इट्स ओके। अगर आप बेटर कर सकते हो तो ठीक है।
अभी तो मुझे पता नहीं है, कैन आई ट्राई इट इन द नेक्स्ट क्लास?
ओके, तो अभी आप कर दीजिए, जितना आप कर सकते हैं उतना कर दीजिए, बाकी नेक्स्ट क्लास ट्राई कीजिएगा।
ओके
चाहे
ओके
तो और ज़ूम कर सकते हैं, देखिए साइड में मार्जिन काफ़ी छूट रहा है और
ओके
अपने हिसाब से ये बॉर्डर है ना, ये और ज़ूम कर लीजिए, बस इतना चल जाएगा।
ओके ओके
ठीक,
ठीक है
और थोड़ा-सा ज़ूम आउट कर लीजिए, ये एरो के अंदर ही रखिएगा बस, ठीक है?
ठीक है।
जो एरो, हाँ, बस। तो अब अपने हिसाब से आप कंट्रोल ले लीजिए। फिर से एक्सप्लेन कर दीजिए प्लीज़,
हाँ ठीक ठीक ओके
ठीक है? मैं म्यूट हो रहा
ओके
हूँ।
okay. So hello everyone. My name is Varat Tau, and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So I welcome you all to the first class of structure of atom. So this is the first class. The chapter which we are going to study is of atom. So this is a second class. This is the second chapter of chemistry of NCERT syllabus, and we are going to cover this chapter in upcoming lectures. So I've divided the whole chapter into 12 weeks or 12 classes. Okay, each class will be of 1 hour, and at the end of each class I will be giving you DPP, that is daily practice problem, and you have to solve these questions and come prepared in the next class. And if you have any doubt, you can ask me, okay, at the starting of each class. Okay, with this said, let me begin. In the next few classes, we will discuss about the fundamental particles that constitute everything around us. Whether you see whatever you see around us, whether those are living beings or non-living things, or a piece of wood or a piece of metal or anything. So these fundamental particles are nothing but the building blocks using which the entire universe has been created. So in this lecture, we will see the properties of these fundamental particles. So what we will cover? Fundamental particles. What are the fundamental particles? Question mark. We learn about how they are discovered, how these fundamental particles are discovered, what are the stories behind it. So this is the scope of this class. So let us begin. So in the last 200 years, scientists have made significant progress in obtaining very clear understanding of structure and properties of the matter. Okay. So mainly the Greek philosophers and Indian philosophers have been wondering about these atoms. So the existence of atom has been proposed since the times of early Indian and Greek scientists. So what they used to think is, let's say they have a piece of, let's say, iron bar. They used to think that we can cut this iron bar into two pieces, right? As this you can do. This can further be broken down into many pieces. Cut down. Like this, we can continue until a stage of uncuttability. A stage of uncuttability is achieved. And this is what is called as the Greek philosophers. The ancient name for atom given by Greek philosophers is atomio, whereas the name given by Indian scientists is Parmanu. So in this class, so there are mainly four theories of atoms are there. Four theories of for discovery of atom. Those are number one, Dalton's theory. Second one is J.J. Thomson's discovery of electrons. Then James Chadwick's discovery of neutron. Further, Rutherford's discovery of protons, and finally Bohr's model of atom. Right. So we'll start. So this will be the scope. Okay. So we will first start with Dalton's theory. Dalton's theory of atom. So Dalton's theory is the most easiest theory. According to this theory, what we have is, okay. So according to Dalton's theory, what we have is atom is an indistinguishable. Atom is uncuttable, or atom can never. Atom is the fundamental particle. Fundamental particle, all substances, and it cannot be broken down. Cannot be further divided. That means according to this theory, no existence of subatomic particles like protons or electrons or neutrons is possible. Okay. So Dalton, but however, the advantages of Dalton's theory was that Dalton's theory was able to successfully explain the laws of chemical combination. Successfully explain laws of chemical combination. Like for example, so before this, let me first. So according to this theory, we can have an, let's say, different atoms can be different. Like for example, we have a atom of iron will be different from atom of cadmium, which will be different from atom of hydrogen, right? So we can have different atoms, right? Hence, because of this, what it was able to do is it was successfully successfully explain the laws of chemical combinations. Like for example, let's say we have an atom type A is combining with two atoms of atom type B, resulting in the formation of, let's say, AB2, right? So this is what atom type 1. Okay, let me, this is atom type 1, this is atom type 2, and this is atom type 3. So two atom types giving rise to third atom types. Okay. However, it was not Dalton's theory was not able to explain disadvantages, unable to explain how chemical combinations, or should I say unable to explain, unable to explain the methodology or mechanism of chemical combinations or reactions. Further, it could not explain, unable to explain the electrical, unable to explain the electrical nature, of materials or matter. And even before the Dalton came, it was well established that uh, when glass or ebonite rod is rubbed with silk or fur, it generates electricity. Like for example, here we have this is a glass rod, and this is a silk material, silk cloth. So when these two are rubbed, it was well established that this results in the formation of positive charges here and negative charges here, right? That is the concept of static electricity was well known. And because in Dalton's theory, atom is a neutral, and it cannot be broken down into subatomic particles. The static electricity cannot be explained using Dalton's theory, right? So this static electric charges was the concept of this was given by Michael Faraday in 1830, right? So according to this Faraday's law, so we will do this one. According to Faraday's law of electro sorry, electrolysis. We already knew that if a fixed amount of electricity is passed through a cell, then it produces a fixed amount of a particular substance at the electrodes. So I will explain its meaning. And the other law was that the number of moles of various substances, the number of moles of various substances liberated at the electrodes by a fixed quantity of electricity are in the ratio of small integers. Okay, so what do we mean by this? For example, what we have is when 96,500 coulombs of electricity when 96,500 coulombs of electricity is passed through a cell containing pure sodium, a cell containing fused NaCl. NaCl is nothing but common salt, right? Then what happens is 1 mole of sodium is deposited at the cathode and half mole of chlorine gas is evolved at anode, right? So this kind of a behavior could not be explained by Dalton's theory, right? So this was the major drawback of Dalton's theory, which was further. So Sir J.J. Thomson, okay. So we'll go to the next theory, that is discovery of electron. Right? So these questions could not be answered by Dalton's theory, and hence scientists all around the globe were trying to figure out a better theory which could explain this behavior. And everybody thought that atom should be subdivided, and it should have fundamental particles like positively charged particle and negatively charged particles. And this was the experiment to perform to find the electrons was done by Sir J.J. Thomson. J.J. Thomson, right? J.J. Thomson's experiment, which so this experiment discovered electrons. Yeah, this is also called as E by M experiment, or we'll discuss it later. Okay, so according to, so this was done in around 19th century. So what this, so these experiments were known as discharge tube experiment. So these experiments are known as discharge tube experiments, right? So how were these experiments performed? So what we have is, under ordinary conditions, gases are poor conductors of electricity, right? However, when a high voltage is applied to them at a very low pressure, these gases become conductors and electricity begins to flow in the form of rays. These rays are called as cathode rays, right? Cathode rays. These are negatively charged rays, right? So the existence of these rays were shown by scientists like Plucker and Crookes, but the main credit goes to J.J. Thomson's, right? Because he studied the properties of cathode rays in detail, which led to the discovery of electrons. Actually, it led to the discovery of electrons as well as E. Okay, so we'll discuss it later. So the experiment is like this. So now we'll discuss the experiment. Right. So let me first grab the image. Okay. So how this was done is, okay. So how was this done is, there was a tube like this. Right. Okay. And then there was this cathode. Okay. And anode. And these were connected in the circuit. Right. This was negatively charged. This was positively charged. And this is connected to an external circuit. Right. And this was connected to vacuum pump. Right. To vacuum pump. And this was filled with gas, right? So this tube was filled with gas particles, right? So the blue one is gas particles, and to control the pressure inside this gas tube, what the equipment was connected to vacuum pump, right? And this is a cathode. Okay, so this is cathode, and this is anode. Okay, right? So what was done is, the when so these gas particles were exposed to high voltage gradient, and simultaneously the pressure inside the tube was also varied. So the observations which were obtained from this is, these are observations were the so what basically was done. So before this, what was basically done was that the gas inside the tube was exposed to high voltage and low pressures. Okay, so the observations was that, number one, initially what was done, only the voltage was changed and pressure was kept as a normal. Okay, so when this was done is, when this was done, what we observed was that the gas remains non-conducting, right? So in words, this can be explained as, when, so let me write observations. Observations. So first observation was that first observation, when the discharge tube containing gas was kept at normal pressure, that means pressure was not reduced, right? Normal pressure, nothing is observed even when the gas or the experimental setup and let's write gas only. Gas was exposed to high voltage. Exposed to high voltages. So voltages, when we say high, it was around 5,000 to 10,000 volts, right? And it is irrespective of the which gas they have taken, right? So Sir J.J. Thomson had conducted similar experiments for many gases, and these are the general observations which were obtained, right? So irrespective of the voltage exposure, at normal temperature, the gas remain unionized. That is, the gas remains non-conducting. Remains non-conducting. Right. So this was the first observation which was obtained. Okay. Second observation. So till now you have any doubt? Anybody has any doubt? Okay. So the second observation which was obtained was that when the, so in second observation, what was done? The pressure was also reduced and the gas was also exposed to higher voltage gradients, right? So the pressure, so and what was observed in this case was that the fluorescent, okay. So what the pressure? So in this case, what was in the pressure of the gas inside the tube was decreased by pumping out the gas with the help of vacuum pump, right? Okay, so when the pressure of the gas is decreased to about approximately around 10 to the power minus 2 atm, which is nothing but 1 to 10 mm of Hg. A different observation was obtained, which was the gas became conducting. The gas became conducting, right? So how did they observe this? Is that the gas started emitting the light, right? So how did they observe this? This was confirmed because the gas started emitting light, right? And the color of gas or color of light, color of light emitted by the gas dep- uh, depends depend depended on the nature of gas taken, right? Now when the pressure was reduced to again 10 raised to power minus 4 atm, which is around 0.01 mm of Hg, what they observed was that the glow in the tube stopped, but the gas continues to conduct the electricity, right? Or what we can write here is pressure was further reduced, right? Pressure further reduced to about 10 raised to power minus 4 bar, which is around 0.01 of mmHg, right? What happened was the glow stopped. The glow stopped, but the gas continues to conduct electricity. Right? Moreover, what happened was that the glass tube at the anode. Anode began to glow with a faint greenish color. Right? So how did they observe was how did they do? So what they did is here or so here what they did. So this is cathode, this is an anode. So around this end, they coated this end with a fluorescent, a phosphorus kind of a material, right? Which glows when something hits on it, right? So when the pressure, so to summarize what happened is this was a cathode, right? So this is a cathode, this is an anode. So this cathode, these things is connected to an external circuit, right? This is a cell, and inside this chamber, a gas is present, right? And this whole connection is connected to a vacuum pump to maintain the pressure. So in this whole experiment, what is done is a gas is taken and it is exposed to various combinations of uh, voltages and pressure. So when the pressure, so initially what was done is pressure was kept constant and very high voltage difference was applied. So what happened is nothing happened. The gas remained unionized. That is, it did not conduct any charges. It did not conduct any electricity. Right? The gas remains non-conducting. Right? But when the pressure was pressure was reduced to around 10 raised to power minus 2 atmosphere, which is around 1 to 10 of Hg. The gas became conducting. Right? The gas became conducting. How did they notice it? This was because the gas started emitting light, and the nature of the gas and the light emitted depends on the nature of gas taken. Right? When the pressure was further reduced, note that the voltage difference are very high. Right? The voltage is the same. What happened? The pressure was further reduced to around 10 to the power minus 4 bar. The glow stopped. However, the glow on the anode side of the tube started to happen, right? So this glow started to happen. So how did they know about this glow? So this outer layer of this inner layer of this tube was coated with fluorescent material, which is most likely of which is usually a phosphorus material, phosphorus sulfate or phosphorus based material, which glows when it hits, when any other particle or it was formulated, it was concluded discovery of the tube is due to due to bombardments of the gas by certain rays emitted from the cathode, right? So this was first conclusion which was obtained. Second conclusion was that these rays move from cathode to the anode, right? Third conclusion which was obtained. So further what was done is that, so let me first draw the diagram. So what was done is the flow of current from cathode to anode was further checked by making a hole So I will explain it in the via diagrammatic way in the upcoming slides. Making a hole in anode and putting the tube behind the anode with fluorescent material that is zinc sulfide. Right. Also, when these rays passed, when a certain object is kept, when these rays are flowing, they casted a shadow as well. Right. So these rays were termed as cathode rays. Right. Because these originated from cathode and ended up in anode, these rays are called as cathode rays. So the diagrammatic representation would be like this. This is the way. Right. Here we have cathode. Here we have anode. This is connected to external circuit. Here we have vacuum pump arrangement. Right. So what happened? What must be happening is this is cathode and this is anode. So rays started to travel in this direction. Right. This was the direction of those rays, and when those rays hit this thing, fluorescent material, which is zinc sulfide, right? Obviously, this happened only when it started to glow, right? 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 So these rays are known as cathode rays. Let us now study the characteristics of these rays. Okay, nature of cathode rays. So the first is that the cathode rays start from cathode and move towards anodes. Right? So how did they confirm? How did they confirm this? Is whenever an object was placed inside the tube, it casted a shadow on the wall opposite to the cathode. So during this experiment, what was done is the gas fluorescence only in the region outside the shadow. This experiment showed that the cathode rays travel in straight line, right? And they travel in straight line. Okay. Further, since the shadow falls on the wall opposite to the cathode, it shows that the rays travel from cathode towards anode, right? So how was the experiment done? It was like this. So we again go back to this was our experiment. This is cathode. This is anode, right? Connected to cathode. This is anode. So when a object, let's say for an example, the object is like this, a fan blade like this was kept. So what they observed was that it casted, so we could see a shadow of this, like this, right? So this confirmed that the rays traveled in this direction, right? Like this. Also further, okay, so like this rays traveled, right? So we could obtain shadows till this point, but whereas when it passed like this, here because the fluorescence material was present in here, right? We could see a glow. Glow could be seen. Whenever the object was not in between the rays and the screen, a shadow was seen. So whenever the object was not in between the rays and the screen, a fluorescence was seen. Whereas whenever the object blocked the path of rays, it showed a shadow. So this basically what does this show is this figure shows cathode ray cast a shadow of the object placed in the path, right? The second observation which was made was the rays themselves are not visible to the naked eye, but their behavior could be observed with certain kinds of material. That means this material when hit the fluorescent material, they glow. That is what we are meaning by that. Right? Third one would be cathode rays produce mechanical effects. Right? For example, when this material, when this object when this object was allowed to freely move, right? When it is placed on a hinge, and when these rays hit this material, hit this object started to move, started to rotate, right? This fan started to rotate when it was connected to an hinge, and these rays are allowed to hit it. That means thereby what the only conclusion which could be drawn is these rays are passing on their momentum. They are coming in contact with this fan, they are hitting this fan and changing their momentum, because of which this fan is rotating, right? Then further it was also seen, right? So this was the third observation. The fourth, this is the third nature of cathode rays. The fourth would be in, so this is very important. So let me write it with different pen. In absence, right? In absence of electric or magnetic field. Right? These rays travel in a straight line. Okay. However, whenever electric or magnetic fields are applied, these rays deviate. Like for example, let's take a short. So here we have, right? So whenever there is no electric field, the electric or magnetic field, the rays travel in straight line, right? Like this. However, when there is, let's say, electric field, we can see that the rays deflected in certain direction depends, and the direction of deflection depends on the electric field. Let's say the electric field is like this, right? These rays go like this, right? Like this. Is depending on the electric and magnetic field, the rays goes like this, right? This was the fourth observation. The fifth is, so in this thing, okay. So the fifth one is when the cathode rays produce X-rays. Sorry, when the cathode rays are allowed to strike thin metal foil, it gets heated up. Thus, cathode rays possess heating effects, right? Sixth observation was that the cathode rays penetrate through thin sheets of aluminum aluminum and other materials. And the last but the most important one is the characteristics of cathode rays do not, and let me highlight it, do not depend on the nature of electrodes, and nature of gas present in the experiment. Also, in the next class, we will see how E by M ratio, that is charge to mass ratio for this cathode rays, was obtained. But for the time being, you can note this down, that the ratio of charge to mass, that is charge to mass, is same for all the cathode rays, irrespective of the gas used in the tube, right? E by M charge to mass, same, right? Right. So all these observations all these observations led that cathode rays consist of negatively charged particles, and these particles constituting cathode rays were named as electrons. And thus negatively charged particles, right? So thus the Dalton's theory was broken down, and a new theory which could explain many behaviors was given, right? So in this class, what we have seen is fundamental particles. First of all, what we have seen is we can understand the concept of atoms. Then further, we learned about Dalton's theory, which said atom is fundamental mental particle. Then we saw drawbacks, Dalton theory, right? which give rise to the experiments of Sir J.J. Thomson. These are also called as cathode ray experiments. Cathode ray experiments, right? Then we learned about these experiments, and we learned about cathode rays, and then we understood the properties or nature. Then we learned that atom is atom is not the fundamental particle, but atom can be broken into subatomic particles, and the negatively charged particle, which consists of cathode rays, is what we termed as electron, right? In the next class, now what we will be doing is, let me write it up, this class, this lecture, right? So in the next lecture, what we will be doing is, next lecture, we will be seeing that charge to mass ratio of electron. How was it calculated? What is its value? Then we will so then we will learn about Rutherford's experiment, which its charge to mass ratio, E by M ratio, right? And then properties. So the rays which are associated with the proton are called as anode rays. Its properties we are going to study. Okay. So I thank you all for joining this lecture, and I hope you are able to understand what I am saying. If you have any doubts, please let me know, and I hope to see you in the next class. Thank you. Hello everybody. My name is Bharat Dao, and I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and also a PMRF fellow at IIT Kanpur. So I welcome you all to the second lecture of structure of atom, lecture 2. So before starting lecture 2, let us first discuss what we have covered in the last class. So in the last class, recap. So in the last class, what we have studied is that in the very early around 4,400 BC, since 400 BC, humans have been wanting to study how the matter looks, and the Greek philosopher called the smallest Greek name for atom, Greek terminology for atom was atomio, and the same from Indian philosophy was Parmanu. These were thought to be the smallest uncuttable particles. Then in the modern science, the theory was given by Dalton's theory. Dalton said that the atom are indestructible, and there are no subatomic particles. And he also stated the merits of the Dalton theory was that they were able to, this theory was able to correctly tell the chemical compound formation, right? Chemical exchange, it was able to accurately predict. Then come in around 19th century, Sir J.J. Thomson did the famous discharge tube experiment or cathode ray tube experiment. Cathode ray tube experiments, which established cathode rays and the fundamental particle, cathode rays, and the fundamental particle of which these cathode rays which were made was termed as electrons. These were termed as negatively charged particles, and these were thought to be, right? So remember, so we have in the last class we have done the in detail we have discussed about cathode rays, and we have also studied its properties, that these are negatively charged particles, and in the presence of in the absence of electric and magnetic field, these particles travel in straight line, whereas its motion is affected by presence of electric or magnetic field. Also, we have studied that these produce mechanical effects as well. Okay, so at this point, what we know, that there are negatively charged particles, called as electrons. However, we neither don't know mass of electrons. Also, we don't know the charge of electron, right? That is what we are going to find it out in this class. So what was first done was a set of experiments were performed by which the E by M ratio, or the charge to mass ratio of these electrons were first calculated. Then so this experiment, we will discuss about this experiment in the later part of the lecture. So first you remember that we have E by M ratio was first calculated, and then after this E by M ratio, the charge, the value of E, or let's say here we don't use E, we use Q by M ratio, where Q stands for the charge on electron. Okay, once this was calculated, and then if somehow we are able to calculate either the charge using this ratio, we would be able to calculate the mass, or vice versa. So what was done was the mass experiment by Professor Millikan's experiment gave us the mass of electron, which we call as M, right? This M. So we already know what is Q by M, right? Known from this, right? Now with this, we know what is the value of M. So from these two set of equations, we can calculate the value of Q, that is the charge on one electron, one particle of electron, right? So let us dive into it. Okay. So what was done? So I will first of all let me import a figure. So let me just draw the figure. So what was done? So let me draw the figure. Okay, right. So this is what was the cathode. This was the anode, right? This point A, this is point B, or this point A. This is point B. This is point C. So here on the backup side, we had applied both the magnetic as well as the electric field, right? So this was right. So this was connected to an external circuit, which was also the case similar to the experiments performed by Professor Sir J.J. Thomson, which we have studied in the last class. Here also external circuit was applied. Then a magnetic field with, and so magnetic and electric field both were applied in the perpendicular direction. This was the direction of electric field, and perpendicular to that, the magnetic field was applied, right? So the experiment was performed in the year 1897 by J.J. Thomson. So in 1897, J.J. Thomson determined the ratio of charge of electron to its mass by measuring the deflection under the simultaneous influence of electric and magnetic fields, both of which are applied perpendicular to each other, right? So this is the apparatus for this figure. So this is the apparatus of this figure, in which the magnetic field, this is the north pole of the magnetic magnet, this is the south pole of the magnet. Using this, a magnetic field was applied, and this is a positively charged, this is a negative charge, right? Perpendicular to it, the electric field was applied. So that what happened is, let's say when a beam of particles, in this case electrons, when it passed through this part of the chamber, both the particle was exposed to both electrical as well as magnetic force because of the respective fields. So let's say this is the particle which is under consideration. So the electric and magnetic field, as they are applied to in perpendicular direction, what happened is, and remember there is no gravity involved in here, right? So what happened is the particle was exposed to two types of forces, right? The first force was, let's say, the electric force. Let us denote it by Fe. This was the force because of the electric field, right? Let me write it here, Fe, right? We will just do it like this. Let's say this is the electron. Let's say the electron is at this point, right? Right here, this is what we are considering in here. So this is the electron, and this is the force because of electric field. Okay, so Fe is the force on electron due to electric field, right? And opposite force is the Fm. Let's say this Fm is force on electron due to magnetic field. Let's say the axis which we are considering is this one. This is X, this is Y. No gravity is involved. Gravity is not involved. Gravity is not involved. So what happened? The electric and magnetic field were adjusted so that on this particle both the electric and magnetic field matches, so that it travels in a straight line. So when both electric and magnetic field, or you can say the force due to electric field and force due to magnetic field, both are exactly equal in magnitude and opposite in direction, the particle or the electron traveled in a straight line and it reached to point B on the screen. So remember, this is the screen, right? So this is the screen, fluorescent screen, right? When both electric and magnetic field were in exact magnitude but opposite in direction, the particle traveled in a straight line and reached at point B. However, when the electric field was dominant, right? The magnitude of electric field was greater than magnitude of magnetic field. The particle reached at point A, right? It deviated. So traveled path, hypothetical path would be like this. It traveled in a straight line, right? As soon as it is exposed, it traveled like this, right? When the magnetic field was more in magnitude than the distance, then the particle has traveled like this. So there was a deflection when the magnitude of both the fields are not equal, but whenever they are equal and exactly the direction is opposite, we were able to find that particle traveled in a straight line, right? So by doing a simple force balance, we can find, okay, so the Fe is usually the Fe, that is the force. Okay, so Fe is given by Q, that is the charge on this particle, multiplied by the strength of electric field. Okay, so we are just taking the magnitude, right? And Fm, that is the magnetic force, has been given by mass multiplied by the magnetic field, right? The mod of this thing, right? So when we do the force balance, what we get is, let me do it here, right? Fe magnitude is nothing but Q into E, and Fm is nothing but M into P. So E represents the strength of electric field and B represents the strength of magnetic field, right? As these forces exactly balance out, what we get is Q into E is equal to M into B. What does this give? This gives us Q by M is nothing but B by E, right? So the left hand side that is this part is unknown. Neither we know the charge of the electron, nor do we know the mass of the electron. This is actually what we need to find. Whereas when doing this experiment, we are in control of, can we control the magnetic field? Yes, we can control the magnetic field, right? Can we control the electric field? Yes, we can control the electric field using this, how much voltage we apply, right? So the RHS of this equation is known to us experimentally, and LHS is unknown. So using this criteria, using such kind of an experimental design, J.J. Thomson was able to find the charge to mass ratio of electron. So he conducted these experiments for multiple gases in variety of conditions of electric, by varying the strength of electric and magnetic field, and he was able to achieve that. He was able to establish that the Q by M, or henceforward we will denote the Q as E. So E by M is, it comes out to be approximately equal to 1.75 8820 into 10 raised to power 11 coulomb per kg, right? So this is how the charge to mass ratio of electron was found by Sir J.J. Thomson, right? So let us understand different aspects of it, right? So this apparatus shown in this figure, right? This apparatus shown in this figure. Okay. So a high voltage was maintained between the cathode and the anode and accelerated by a high voltage. So clearly, the cathode rays would emerge from this, okay, consisting of electron. Now let us understand how effects of this. So the magnitude of negative charge on the particles. So greater the, so let me write this down. Okay. Point which is to be noted is greater the magnitude of the charge on the particle, greater is the interaction with the electric or magnetic, right? And there greater the deflection. So when we say about deflection, we are talking about this distance, right? So higher the strength of electric and magnetic field, more will be the deflection, right? It can either go to point A or point C, right? Then mass of particle, let me highlight it, greater the deflection, right? Then the extent of deviation depends on the mass of the particle, right? Which is also intuitive. Greater the mass, lower will be the deflection. Lighter the particle, greater is the deflection, right? For the third point, strength of electric and magnetic field, right? Strength of electric, which we are denoting by E, and magnetic, which is B bar, right? So the deflection of particles from their original path increases with increase in the voltage across the electrodes or the strength of magnetic field. When only the electric field is applied, the electrons deviate from their path and hit the cathode ray tube at point A, right? Right. So we are talking about this. So when only electric field is applied, and magnetic field is not applied, the electrons deviate from their path. So this would have been the path, but in presence of electric field, the path, the particles moves towards point A, right? Similarly, when only magnetic field is applied, the electrons deviate from their path and hit the cathode ray at point C, right? So by carefully balancing the electric and magnetic field strength, it is possible to bring back the particle to the path followed as in the absence of electric and magnetic field, and they will hit the screen at this point, right? So let me write this. When the deflection of the particle from their original path increases with increase in voltage across the electrodes strength of magnetic field. This is the first point which is to be noted. The second point which is to be noted is only electric field is applied. The particles or the electron deviate from their path, that is the straight line, and hit the cathode ray at point A. Similarly, magnetic field is a particle deviate their and cathode ray point, right? So these were the conclusion. So back here, so careful balancing the electric and magnetic, it's possible to part 2 followed by as if no electromagnetic, and this was what was done, and using the force balance we got Fe is equals to Fm, and Fe is nothing but by QE, which is nothing but M into B, which gave us Q by M, B by E, right? So this was the thing. So now what we have is we have the Q by M ratio, right? We have the Q by M ratio of electrons. This is the key result, and this value was found out to be how much? 1.7588 10 raised to power 11 coulomb per kg. Okay? This is a key result that you have to. So now we'll move on to the next part. So anybody has any questions? If nobody has any questions, then we'll move on to the next part. Okay. So now we'll move next part, which determine charge on the right. So the experiment was performed by R.A. Millikan in 1909, right? So in the previous, up till now, what we have used is we have used the gaseous particles, but in this experiments, the gaseous particles was not used. Instead of gaseous particle, what was used was liquid substance was used, and gravity was also used. So up till now, the gravity did not play any role. However, in this experiment, gravity played role. So what happened is electric field was applied in a direction which was opposite to the gravity, and the strength of electric field was maintained so that it exactly matches the gravitational force, and then the force balance was performed, right? The force balance was, let's say this is the drop. So I will show the detailed picture, but just let's say this is the droplet, right? So the electric field was applied in the electric field was applied, so that this is the electrical force, right? This is the direction of electric force, right? Okay, so let us say that this is Z direction and this is Y direction, right? And this electric field was matched with gravity. Let's say gravitational force is this. So Fe bar force balance, right? We already know how the electric force was given. It's given as Q into E, which is nothing but M into G. In this case, as this droplet is liquid, we know its specific density, and also we know the volume of this droplet. Using this, the mass in this case is known, mass of the droplet, which is nothing but density multiplied by the volume of this droplet, and the volume of the droplet will be nothing but volume of the sphere, right? So we know the m, we already know the gravitational constant, right? Acceleration due to gravity, and this is the this is the electrical field, right? So using this, q is equals to m into g by e. So the RHS of this expression, that is m, that is the mass of the droplet, is already known. The acceleration due to gravity is also known, and the strength due to electric field is also known, and hence we can calculate the charge on the electron. So let's show the experimental setup. Right? So this is the experiment. Right? This is a cubical box. Right? This is the particle. Right? So electric field was applied in this direction. This was the direction of gravitational field, and a telescope was placed from which the experiment is. So let me use this. So this is charged or observation. So the charge on electron was measured by R.M. Millikan in 1909 by a method known as oil drop method, right? So this method is oil drop. So this is the apparatus, overall apparatus, right? Small drops of oil in the form of mist are formed by spraying, and these are allowed to fall between the two metal plates, right? So this would be the two metal plates, right? This will be the upper, right? This will be the upper metal plate, which would be charged, and this would be the lower plate, right? So you with the help of these plates, the electric field was applied, right? The oil in the form of mist drops through the air under the influence of gravitational force, right? Then the experimentalist irradiated the space between the plates, that is this place, with X-rays. These knocked electrons out of the molecule. So electrons from this molecule, oil droplet, was removed, thereby making it charged, right? And some of these electrons were caught by oil droplets, which acquired electrical charge. Okay. So by charging the upper plate positive, so this plate was charged positive and the lower plate negative, an electric field was applied in the upper direction, in this direction, right? Let me draw the axis here. So this will be X, this will be Z, right? So by adjusting the electric field strength, the upward electric force, right? This upward electric force on the droplet was balanced against the downward gravitational force. Under these conditions, this droplet remains steady from the amount of charge on the plates and the mass of the droplet. The charge on the droplet was determined. The mass of the droplet was determined from the rate of fall of droplet through the air with the plates were uncharged, right? So from these experiments, right, this found out charge of to be approximately 1.6022 into 10 raised to power minus 19 coulomb, right? So Q was found out, Q or E was found out to be 1.6022 10 raised to power minus 19 coulombs, right? From the experiments of J.J. Thomson, we already knew that E by M is nothing but Q by M for electron was approximately how much? 1.758820 into 10 raised to power 11 coulomb kg inverse. Now we know this E, right? What does this imply? This implies mass of electron. Let us denote by M, which is E divided by E by M, right? We know 1.6022 10 raised to power minus 19 coulombs divided by 1.75 8820 10 raised to power 11 coulomb per kg. So M comes out to be 9.1094 into 10 raised to power minus 31 kg. This is what is to be remembered. So using this, certain observations that were made, right? The first, number one, the mass of electron is much mass of hydrogen the mass is approximately 1/18 the mass of hydrogen, and the most a subatom called which can a unit 1.6022 10 minus 19 coulombs and has a mass of 9.1 into 10 raised to power minus 31 kg equal to 1/1837 the mass of was discovered, right? So let us first discuss how this was calculated, how it was established, how the mass of electron is about 100 and 1837 times the mass of hydrogen atom. Okay, let us discuss this first. Right? Right? Mass of can is 6.10 raised to power, right? That is nothing but Avogadro number. Hence, what 1 gram of hydrogen is approximately equal to 1.008 gram, right? That means 6.022 10 raised to power 23 atoms of 1 gram atom, right? So this is 1 gram atom of, hence 6 10 raised to power 23 at weight 1.008 grams. Hence 1 gram 1.008 divided by 6.022 10 raised to power 23 1 into minus 24 grams, and as 1 kilogram is equal to 10 to the power 3 grams, 10 raised to power mass of 0.94 10 raised to power minus 31 kg, right? Hence is 1.674 10 raised to power minus 27 kg divided by 9.1094 10 raised to power minus 31 kg, which is about 1837, right? An atom 1807, then other way around of saying this same thing would be an electron is has a mass which is about 1/1837 times the mass of an atom of hydrogen, right? So in this class what we have learned is, in this what we have learned is we have found the experiment which was done to find the of charge. Then further we found out how Millikan's experiment. We learnt about Millikan's calculated mass of electron. Using this we calculate the on one electron, right? So in the next class what we are going to study is, right, naturally we know that the things around us are usually chemically neutral. That means the atom has to be chemically neutral, right? So the questions which we will answer is, as there is an electron which is about which is a negatively charged particle and has very less mass, there has to be some particle which we will find that it's called proton, which is a positively charged particle, right? And this similar to how was this discovered? We will see its discovery. It's right. How M was calculated, right? And further we will also study the properties, right? Properties of rays associated with proton. This positively, let's say positive. So these are usually called as anodes, right? Anode rays. Then further we will study about how these are distributed inside an atom. So we will study about the theory that, then we will study about, right, Rutherford's, right? This is what we are going to cover in our next class. Okay. So I hope you are able to understand this lecture, and if you have any questions you can ask, right? And I hope to, and I thank you all for attending this class, and I hope to see you all in the next class as well. Thank you. So I'll be closing the class. So I welcome you all to this third class of the structure of atom lecture. So I am Varat Tau, I am a doctoral student at the Department of Chemical Engineering, IIT Kanpur, and also a PMRF fellow. Right. So let us start. So in the last class, in the last classes, what we have seen is we have seen that around 400,000 BC, Greek scientists as well as Greek philosophers as well as Indian philosophers both independently coined the discovered or hypothesized uh, atom as the fundamental building block. So the name which was given by Greek philosophers was atomio, and the name given to the atom by Indian philosophers was Parmanu. Then further we saw that in around 1808, Dalton came up with the first theory of atom for the in the modern science, and then we studied about his theory and his drawbacks. And then later we studied about the cathode ray tube experiments performed by J.J. Thomson, which which discovered a certain type of rays called as cathodic rays, and these experiments also discovered a fundamental particle, a subatomic particle, that is electron, and thereby finding an error in Dalton's theory, and hence Dalton's theory was no longer valid, and there was a need for an alternative or the upgraded theory. So cathode rays was discovered, and we also studied the properties of these cathode rays, and we also discovered that these are negatively charged particles, and these also have energy. Then they move from cathode to anode. This we have studied, and then we established that subatomic particle called electron is present. And then further, we studied how this charge to mass ratio of electron can be found out, and then we further studied the Millikan's experiment, Millikan's oil drop experiment, by which we calculated the mass of electron. And since we already knew the charge to mass ratio from previous experiments, and now with Millikan's experiment, oil drop method, we could find the mass of the electron, thereby finding the mass of electron, right? So this is what we have studied in the class. So in this class, what we are going to study is we are going to study the anodic rays, right? So since it was cathodic ray was discovered and electron particle was discovered, it was highly hypothesized that a positive particle, which was later discovered as proton, should also be present, because atom in a whole is neutral. So that is what we are going to study, right? So let me first write recap. Lecture 3, structure of atom. The first topic which we are going to study is discovery of protons, positively charged particle. The presence of negatively charged electrons in an atom suggested that there must be some positively charged particle, because the atom on the whole is electrically neutral. In 1836, Goldstein discovered that in addition to cathode rays, a new kind of rays are also found streaming behind the cathode rays in discharge tube experiments, right? And these rays traveled in the direction opposite that of cathode rays, right? So the experiments which was done, which was performed by J.J. Thomson, we know that this experiment gave rise to discover the cathodic rays. But on close analysis of the same experiment was done by Goldstein in 1836, right? Goldstein discovered anode rays, right? So he did the close analysis of the same experiment performed by J.J. Thomson, thereby discovering a anodic rays, and these anodic rays travel in a direction opposite to cathode rays, and have also negative charge opposite to anode rays, right? So let me do it. So this is the experiment. So this is a pictorial representation of the experiment performed by Goldstein. So so if you can remember, in the last class we have seen that this was the cathode. This was the tube which in which a gas was present, and this whole setup was exposed to a very high potential and a very low pressure, right? So low pressure was maintained with the help of vacuum pump, and high voltage was maintained by using this thing, by using these cells. And then this is the perforated cathode, right? And this is the anode, and the anode rays travel from negatively charged electrode, that is the cathode, to positively charged electrode, that is anode. So this is the direction of cathode rays, right? We have seen. And but close analysis of the same experiment revealed that in the direction which is opposite to cathode rays, so this is the direction of cathode rays, and in direction opposite to cathode rays, that is this direction, anode rays could also be found, right? So by this way, E. Goldstein in 1836 discovered anode rays, right? So now we will see about the properties of these anode rays. Characteristics. Right? So these rays are also deflected by magnetic and electric field like cathode rays, but the deflection of anode rays is in direction opposite to that of cathode rays, right? This means that these rays consist of positively charged particles and were also named positive rays or canal rays or anode rays, right? The characteristics are follows. The anode rays travel in straight line, which is expected, and cast shadow of the object placed in their path, right? Second characteristic is the anode rays are deflected by magnetic and electric field, just like cathode rays, but the deflection of anode rays is in a direction opposite to that of cathode rays, right? Anode rays are deflected by the magnetic as well as electric field like cathode rays, but the deflection is deflection of anode rays is in opposite direction to that of the cathode rays, right? So in order to show this, let me grab a picture, right? So here, right, you can see, right? So these are the anode rays. So when these anode rays are exposed to electric field, so this is the positively charged electrode, this is the negatively charged plate. So when these anode rays are exposed to electric field, the path, if the electric field would not have been present, the path would have been like this, right? But because the path is because electric field is exposed, anode rays are exposed to electric field, the path would change. Now because these rays are positively charged, you know, they will get attracted to a negatively charged electrode, and hence the path is like this, right? These anode rays are deflected towards negatively charged particles, right? For cathode rays, for cathode rays, the path would have been like this, right? The deflection would have been like this. So this is cathode rays, and this is anode rays, right? The third characteristics of this these rays. Like cathode rays, these rays also rotate the paddle wheel placed in their path and also have heating effect, right? So like cathode rays, these rays also rotate the wheel placed in their path and also have heating effect. Right? The fourth characteristics is the charge to mass ratio for these rays is considerably smaller than electrons. Right? The charge to mass ratio for these rays is considerably smaller than electrons. Right? Right? The fifth and last point is, unlike cathode rays, the E by M ratio, that is the charge to mass ratio of positive rays, depend upon the nature of gas taken in the tube, right? So unlike cathode rays, the charge to mass ratio of positive rays depends upon the nature of gas taken in the tube. Right? It depends upon, right? It depends upon the nature of gas. This is very important thing which is to be highlighted, right? Now let us understand how the charge to mass ratio of particles which consist of anode rays was computed, right? So by means of deflection in electric and magnetic field, which is similar to what was done for the calculation of charge to mass ratio of particle of cathode rays. The charge to mass ratio for this anode rays was also found out, right? So by means of deflection in electric and magnetic field, charge to mass ratio of particles constituting anode rays was determined for different gases in the same manner, right? As for cathode rays, it was found that the value of E by M for these rays is not constant and is considerably smaller than for electrons. Unlike cathode rays, the charge to mass ratio of anode rays was found to depend upon the nature of gas taken in the discharge tube. This is obvious because positively charged particles are produced by the loss of one or more electrons from the neutral atoms of the gas contained in the discharge tube. Therefore, the mass of positively charged particles will depend upon the nature of the gas. In case of hydrogen, the charge to mass ratio was maximum. Right? So let me write this down also. Right? So the charge to mass ratio of particles constituting anode rays. Right? So the conclusions which were obtained was, unlike cathode rays, or we can write that E by M, that is charge to mass ratio of particles constituting anode rays was variable, right? And it uh, E by M ratio was smaller than electron, right? And depends upon the gas undertaken, right? Gas undertaken is smaller, right? Now let us discuss the reason for this. This is obvious because positively charged particles are produced by loss of one or more electron from the neutral atoms of the gas contained in the discharge tube, right? And hence the mass of positively charged particle depends upon the nature of gas, right? So in case of hydrogen, the charge to mass ratio was found out to be maximum, right? And the value was around 9.58 into 10 raised to power 7 coulombs per kg, right? Okay. Its charge has been found out to be 1.6022 10 raised to power minus 19 coulombs, right? Which is equal to the magnitude but opposite in sign to that of an electron. That is 1 unit of positive charge, right? Since E by M ratio is maximum for hydrogen, the mass of positively charged particle obtained from hydrogen is the smallest, and hence its mass can be calculated from this, right? So what we know is for hydrogen, we know E by M is around 9.58 into 10 raised to power coulombs per kg, right? And we also know unit positive charges is E is nothing but 1.6022 10 raised to power minus 19 coulomb. Hence M is nothing but E by M, which is nothing but 1.6022 10 raised to power minus 19 coulombs divided by 9.58 10 raised to power 6 coulombs per kg, which is 1.67 10 raised to power minus 27 kg, right? So this mass is about, right? So this mass is about 1837 times the mass of electron, right? Hence, what we can write about proton. So this positively charged particle is termed as proton. Thus, a proton is a subatomic particle which carries one unit positive charge, right? Which is 1.6022 10 raised to power minus 19 coulombs and has a mass of 1.67 10 raised to power minus 27 kg, right? So it has been observed that the mass of positively charged particle was 1 unit mass or 1.67 into 10 raised to power minus 27 kg only when hydrogen was used, right? For other gases, it was found that this value was equal to the whole number multiple of this value, right? That is mass of proton. This means that the atom of other gases consists of 2 or more protons, that is multiple protons, right? So till now what we have studied is, we have studied that in discharge tube, cathode rays are emitted from cathode. These rays consist of stream of electrons which move towards anode with very high speeds. When these fast moving electrons strike the atoms or molecules of the gas contained in the discharge tube, they knock off one or more electrons. The removal of electrons from neutral atoms or molecules of the gas results in the formation of positively charged ion. These positively charged ions move towards perforated cathode and constitute a beam of positive rays or anode rays coming through the holes of cathode. These charge ions carry various amounts of positive charge depending upon the number of electrons lost by the corresponding atoms or molecules, right? So in summary, right, what we have studied is, number one, we have studied that in discharge tube, cathode rays are emitted from the cathode right? These rays consist of stream of electrons which move towards anode with very high speeds. When these fast moving electrons Strike the atoms or molecules. Of gas. Contain in the discharge tube. Right? They knock off one or more electrons. Right? The removal of electrons from neutral atoms or molecules. Of gas results in the formation of positively charged ions. These positively charged ions move towards perforated cathode and constitute the beam of anode rays, right? Right? These charged ions carry various amounts of electrons lost by the corresponding atoms or molecules. Right? This is what we have discovered. This is the summary, right? So now let us discuss the arrangements of electrons and protons in an atom, right? The next topic is arrangements or arrangement arrangement of electrons and protons in an atom. First we'll study about Thomson's model, right? Okay. So after the discovery of electrons and protons, scientists started thinking of arranging these particles in an atom. So different models were proposed to explain the distribution of subatomic particles in an atom. The first simple model was proposed by J.J. Thomson, known as Thomson's atomic model. Right. So J.J. Thomson proposed that an atom consists of a uniform sphere in which positive charge is uniformly distributed. The electrons are embedded into it in such a way as to give the most stable electrostatic arrangement, right? So, right, what did Thomson said is, he proposed that an atom consists of a uniform sphere in which positive charge is uniformly distributed, right, and electrons are embedded into it in such a way as to give the most stable electrostatic arrangement, right? So this was the model which was proposed by Thomson. So this is a representation of atom, a spherical particle, a sphere, and its radius he gave as approximately 10 raised to power minus 10 meter, around 1 angstrom, and which is equal to the size of atom. This model was much like, so here you can see, so the blue region is the positive sphere which is uniformly distributed, positive charge which is uniformly distributed, and this here represents the negatively charged electron, right? So this model was much like pudding or a cake embedded with resins. Therefore, this model is also known as plum pudding model, right? This model was also compared with watermelon model of positive charge, in which seeds, that is electrons, are embedded. Therefore, this model is also given different name such as resin pudding, plum pudding, or watermelon model. An important feature of this model is that the mass of atom is considered to be evenly spread, right, around the atom. So this model explains some of the known properties and electrical neutrality of atom. However, it was soon discarded when Rutherford and his co-workers observed unusual scattering of alpha particles by the thin metal foils. Since this model could not explain the experimental results, it was then rejected, right? So this model is also called as also called as plum pudding model or watermelon model. Right? Advantages of this model. This model explains the some of the known properties and electrical neutrality. Of atom. What is this disadvantage? Or is it? Could not explain the experimental observations of Rutherford gold foil experiment. Right? Hence, there was a need to found and update. There was a need to update the model. So Rutherford scattering experiment. So let us discuss about it. So in order to understand the arrangement of electrons and protons in an atom, Rutherford and his student in 1909 performed a series of experiments known as Rutherford scattering experiment. In their experiments, they bombarded a target atom by subatomic projections. Right. So to understand this, let us draw a picture. Right. So this is a picture of Rutherford experiment. In this, what they did, they took a radioactive material and they embedded that material in a lead box so that the radiations could travel only in particular direction and not in all the direction. Hence, these slits were also placed to ensure that radiations travel in this direction only. And the radius consists of an alpha particles. So alpha particles are nothing but positively charged helium. So positively charged helium, that is helium 2 plus. So it carried uh, twice the positive charge of on helium atom, and this passed, and then this is the thin gold foil which was placed. So these radiations were bombarded, and it was found that the radiations which was oncoming were scattered. Right. So these were the directions of radiations after they hit the gold foil, and this is the fluorescent screen, and observations are being made from there. Right. So in this experiment, a piece of radioactive substance, that is radium, is placed in a lead block. The block is constructed in such a way with slits that only a narrow beam of alpha particles could escape. The beam of high energy alpha particles was directed at the thin gold foil. The thickness of the gold foil was about 100 nanometers. So in order to detect the alpha particles after scattering, a movable circular screen was coated with zinc sulfide is placed around the gold foil. Right. So when alpha particle strike the zinc sulfide screen, right, this particle flashes of light which can be detected by examining different portions of the screen. It was possible to determine the proportions of alpha particles which got deflected through various angles. Right. The observations are as follows. Observations. So the first observation was most of the alpha particles, that is around 99%, passed through the gold foil. Gold foil undeflected. Right. Second one is a small fraction of alpha particle got deflected through small angles. Third observation was very few, about 1 in 20,000, did not pass through the foil. right, at all, but suffered large deflection right, more than 90 degree or even more, or even came back, suffering a deflection of 180 degree, right? So let us understand the observations from image deflection. So you can assume that this is the gold foil, atoms of the gold, right? So most of the deflections, that is around these rays A called. So these are the rays which traveled. Most of the rays traveled undeflected. Only some, that is B, got a deflection, right? So these are the deflections, right? And then very small atoms rebounded, right? Rebounded or suffered a large deflection, right? So if the Thomson's model would have been correct, then the deflection would have been like this, right? Right? This is the Thomson's model, in which this is the atom. A positive charge is uniformly distributed throughout the atom, and the negative charge electrons are embedded in it. So if the Thomson's model would have been correct, so then particles would have, like alpha particles would have come in this way and got deflected like this, right? So we would have seen a lot of deflection, right? Deflection of this pattern, right? So now according to Thomson's model, if positive charge of the atom was uniformly distributed, then positive charge alpha particles with a considerable mass would pass through the weak electric field, largely undeflected or slightly deflected, right? However, the observation which he noted was completely different, and hence Thomson's model could not provide answer for this observation and therefore was discarded, right? So how did Rutherford explain, right? How did he Rutherford explanation, right? Explanation of observations, right? So since most of the alpha particles passed through the gold foil and deflected, it means that there must be very large empty space, right? Very large empty space. Number 2, alpha particles are positively charged and have considerable mass. Hence, they can be deflected. Only if they come close to some heavy positively charged mass due to enormous field of repulsion. Since some of the alpha particles are deflected to certain angles, it means that there is a heavy positively charged mass present in the atom. Moreover, this mass must be occupying a very small space within the atom, because only a few alpha particles suffered a large deviations, right? Let me write this down. there is heavy positively charged mass present in the atom, right? Moreover, this mass must be occupying a very small space within the atom. Because only a few alpha particles suffer a large deflection, right? The third one, that the strong deflections or even bouncing back of alpha particles from the foil were explained to be the direct collision with heavy positively charged mass. Right? This positively heavy charged mass, which occupies only a small volume in an atom, is called nucleus. So based on the basis of above experiments and observation, Rutherford proposed a model for structure of atom called Rutherford's nuclear model, right? Rutherford's atomic model. So the main features of this model are: in an atom, the entire mass and the positive charge is concentrated in a very small region at the center known as nucleus, and it was observed that the volume occupied by the nucleus is negligibly small as compared to the total volume of atom, right? So in an atom, the entire mass and the positive charge concentrated in a very small region at the center known as nucleus, and it was observed that the volume occupied by nucleus is negligibly small as compared to the total volume of atom, right? The second observation which was made was the positively charged, the positive charge of the nucleus is due to protons and the magnitude of positive charge on nucleus is different for different atoms, right? The magnitude of positive charge on the nucleus is different for different atoms, right? The third was the mass of nucleus is due to protons and some other neutral particles, each having a mass nearly equal to the mass of proton. This neutral particle was discovered later on by Chadwick in 1832, right? The mass of nucleus is due to protons and some other neutral particle. Right? The fourth conclusion was the nucleus is surrounded by negatively charged electrons, which balances the positive charge on the nucleus. Thus, the atom is electrically neutral. Right? The nucleus is surrounded by negatively charged electrons, which balances the positive charge of the nucleus. Yes, thus the atom is thus making the atom electrically neutral. Right? The fifth observation was the electrons are not stationary but are revolving around the nucleus at very high speeds, like planets revolving around the sun. Right? The electrons are not stationary but are revolving around the nucleus at very high speeds. Right? Thus, the Rutherford model, the electrons and neutrons are held together by electrostatic force of attraction. The electron and protons are held together strong electrostatic force of attraction. Right? And the last one was most of the space inside the atom between the nucleus and the revolving electrons is empty. Right? So these were the observations. These were the Rutherford. These are the Rutherford's new nuclear model of atom. Right? So in summary, what we have learned is right? What we have learned is, we have learned about anode rays, right? Anode rays, we have learned about the Q by M ratio of anode rays, how anode rays were discovered, what is the charge on anode rays, what is the mass of atom anode rays, characteristics of anode rays, right? Then we studied about arrangement of atoms, right? Arrangement of subatomic particles in an atom. That so we studied Thomson's model. Then we studied the advantages and disadvantages of Thomson's model, and then we learned about Rutherford's gold foil experiments and its observations, and finally we established Rutherford's nuclear model of. So thank you all for attending this class, and hope to see you again in the next class. Right? Thank you.